So this is 7.3, the product and quotient laws. So in the previous class, we derived the product rule of logarithms, and that said the log of a times b can be broken into the log of a plus the log of b, and vice versa. If you had two logs, you can simplify it. If two logs are being added, you can simplify it into the log of the multiplication of each of their arguments. Similarly, there exists a quotient rule where the log of some value a take away the log of some value b equals, and it can be simplified into a single log where the argument is a over b. And then in previous classes, we looked at things like the power rule, where you can move the exponent inside the argument to the front of the logarithm, as well as the change of base rule. So we're going to take these four rules and look at some more logarithm examples, where we are going to be simplifying using the laws of logarithms, and also evaluating. So looking at the first example, log of 32 minus log of 8, this is an example where we have two logarithms being subtracted, and we can most certainly apply the quotient rule for logarithms in simplifying this. And so we could state here that this would be the logarithm of 32 on the top divided by 8 on the bottom. And then you can use the calculator to evaluate this. We'll just simplify it with one more step. So 32 divided by 8 is 4, so the log of 4. And on the calculator, log of 4 is equal to 0.602 if I round it to 3 decimal places. In the next problem, we have the logarithm product rule for logarithms, where we have two logarithms being added. And remember, these are logarithms with the same base, right? So they must have the same base. You can't add logarithms of different bases using that product rule. So the logarithm of base 5 of 20 plus the logarithm of base 5 of 3. And I can add these together to write a single log of base 5, where I'm multiplying these arguments 20 times 3. And that's going to be 60. So log base 5 of 60. And to evaluate this to 3 decimal places, I'm going to need to apply the change of base formula. I want to express this using power of 10, because that is what our calculators work on. So we have the log, applying the change of base formula says you take the log of the argument, log with a base 10 of 60, and divide it by the log of the previous base. And so here we have log of 60 over log of 5, which now we can put in our calculators to get the result of 2.544. Okay, moving on to another example. Simplify and state any restrictions on the variables. So here I can use a couple of logarithm rules in this kind of question, where you have multiple logarithms here. All of them have a base of 4. If you see that there's a base 4 in each of these terms. And so let's apply the logarithm rules for this question. Okay, so I can first start by looking at the first two terms, and I can apply the product rule for logarithms and write this as the log of base 4 of x times 2y. And I'm just going to write this with the number first, so 2xy. And that's subtracted by the log of base 4 of z minus 3. And now I have two logarithms that are being subtracted, so I can apply the quotient rule here. So I can write this as a single log of base 4 of 2xy divided by z minus 3. Okay, and the order counts which one becomes a numerator and which one becomes a denominator. It's the first logarithm that will have the argument be in the numerator, and the second logarithm that's being subtracted will have its argument in the denominator. Okay, now let's look at restrictions. Now remember, the logarithm, so the log of any argument, right, that argument has to be greater than 0, right? It cannot be negative. So I'm going to look at each of these logarithm terms, right? And you're going to look at, okay, well, this argument cannot be negative, so that means x is greater than 0, right? And 2y, that cannot be negative, nor can it be 0, right? So you cannot have, you cannot raise 4 to some power to get 0. So each of these terms have to be greater than 0. So 2y has to be greater than 0, so that means y is greater than 0. And the last, our logarithm here, z minus 3, here z minus 3 has to be greater than 0, and so z is greater than 3. So state the restrictions when told to do so, and here they are. Okay, looking at the next example. Log of a minus 2 log of b plus 3 log c. So if I look at the first two logarithms, you cannot apply the quotient rule just yet. We're going to kind of look at the power rule in reverse and rewrite the question as log of a minus log of b squared. And then for that third term, I can do the same thing, log of c cubed. So kind of going using the power rule in reverse. And now I can apply the logarithm rules for the quotient rule and the product rule. And I'll start with the quotient rule for the first two terms. Log of a minus log of b squared can be written as a single log of a over b squared. And then I still have plus log of c cubed. And then I can combine these two terms using the product rule and state the log of a over b squared times c cubed, or I can say a c cubed over b squared. Okay. You can also, if you're adept enough, you can do this kind of one step. That's fine too. But I would like to see the steps too. So that would be very nice to see. B, restrictions. So A, B, and C. So what are these restrictions? Well, the argument for A has to be greater than 0. And the argument for B, this one here, has to be greater than 0. And C also has to be greater than 0. Okay, let's look at another one. Number 3, evaluate using logarithm rules. Okay, so why don't I look at, we have 4 logarithm terms here. Let's look at the first two. We can apply the product rule here because we have 2 logs being added. So let's say that we have log of base 6 of 4 times 6, right? 4 times 6 plus these 2 logarithm terms are being subtracted. So I can write that as log of base 6, and using the quotient rule, write the first one as the numerator 3 over the denominator 2. Okay. And then 4 times 6 is 24. And I have 2 logarithms here. Both of them still have the same base, which is 6. So write it as one logarithm. And we can do 4 times 6, which is 24, times 3 over 2. So that is the product rule. And then I can kind of simplify this a little bit more. 24 over 2 is 12. 12 times 3 is 36. So the log base 6 of 36. And that turns out to be a nice number, right? So that can be written as, that answer is 2, right? That's going to equal to 2. So that's like saying, well, 6 squared equals 36. So that evaluates to 2. All right, let's look at another one. Log 3 log base 3 of 3 minus log 3 base 3 of 4 plus 2 times log base 3 of 6. Okay, so I can write this first using the power rule in reverse. So log 3 of 3 cubed minus log base 3 of 4 plus log base 3 of 6 squared. So just taking these coefficients and bringing them back to the inside of the logarithm argument as the exponents, just the reverse power rule. And then we can combine our logarithms. Log base 3 of quotient rule, 3 cubed over 4, and that plus log base 3 of 6 squared. Combining the logs with the product rule, here we have now 3 cubed times 6 squared over 4. And that gives us 3 cubed is 27, 6 squared is 36. 27 times 36 divided by 4 would be 243. So log base 3 of 243. And that turns out to be 5. Right? 3 to the power of 5 equals 243. Okay. Let's look at another question. Number 4, simplify and state any restrictions on the variables. So now I have something with some x's in here. Well, let's talk about some restrictions, right? So the arguments of each of these logs, well, they have to be greater than 0, right? 2x minus 6 has to be greater than 0. So that means x would have to be greater than 3. For the second term here, x minus 25 is greater than 0. So x would have to be greater than 25. And for the last one here, x minus 1 greater than 0, then x has to be greater than 1. Unlike the other questions we had previously, this question has x in every single term, right? It's not a, b, c. It's all x and x and x. So these restrictions, well, one of them will dominate over the other ones. And it turns out that this one dominates, 25, right? This one must have x greater than 25. So if I use anything that fits between 3 and 25 or 1 and 25, that won't work, right? I can't put in 5 because then 5 minus 25 is a negative, right? So although x equals 5 could satisfy this term and it could satisfy this one, log of x minus 1, that x being 5 would not satisfy the middle one. So the restriction that dominates is x greater than 25. Okay, so that's the restriction that we will use for this question. Now, in terms of simplifying it, let's work on that. So I can apply the product rule in the first two log terms here. So the log of 2x minus 6 times x minus 25, and then minus log of x minus 1. And then I can apply the quotient rule and state one single log here, log of 2x minus 6 times x minus 25 over x minus 1. Okay. We could, of course, expand the top if we like to see if there's any terms we could look at maybe canceling with the denominator if there is, right? So if we expand the top, it would be 2x squared. Minus 6x minus 25 times 2 is 50, so minus 56x. And then 6 times 25 is 150, so plus 150, all divided by x minus 1. And then we can leave the logarithm as that. Okay, looking at the next question, log base 2 of x squared minus 5x minus 6 minus log base 2 of x minus 3. Okay, so a couple of remarks here. So this argument, x squared minus 5x minus 6, well, that we want, if you're looking about restrictions, right, x squared minus 5x minus 6, that has to be greater than 0. And x minus 3 also has to be greater than 0. So one restriction from the x minus 3 is simply x is greater than 3. Okay, now how do I figure out the other one? Quadratic greater than 0. Well, we could factor it, right? X minus 6 and x plus 1. That has to be greater than 0. Okay, and oh, well, have a look. If I made what are my roots for this one here? X equals 6 and x equals -1. If I made a little chart, -1 and 6, and I looked at what's happening that's when x is less than -1, -1 and 6, and x greater than 6, do I get a positive or negative? So for numbers that are less than -1, if you use a test value of -2, then -2 minus 6 is a negative number. -2 plus 1 is a negative number, and together that makes it positive. and you're choosing a number between -1 and 6. Well, I can pick 0, and then so 0 minus 6 is negative, 0 plus 1 is positive, that makes it negative, so I can't use that interval as part of my restriction. And then x greater than 6, if I put 7, 7 minus 6 is 1, and 7 plus 1 is positive, so positive, positive is positive. All right, so the intervals that give me a positive greater than 0 is x less than -1 and x greater than 6. Remember, from this restriction, x has to be greater than 3, so I can't use x less than -1. Okay, and I can't use, well, I can't use x equals 4 or x equals 5 because that wouldn't satisfy the middle condition. It'll make it negative, right? That interval between -1 and 6 is negative. So if I put an x equals 4 or x equals 5, then the logarithm of this would be ending up negative. So that doesn't work either. So what ends up dominating is this condition, x greater than 6. So that's going to be, that will serve as the restriction for this question. Okay, so let's look at simplifying now. So we can rewrite the logarithm, the first original question. It's being subtracted, so we can apply the quotient rule. So log base 2 of x minus 6 times x plus 1. I'm just writing it already in the factored form, divided by x minus 3. Okay, and so there you have it. And so the restriction is x has to be greater than 6. Okay. All right, let's look at another example. You can try the U-try question if you like, but let's move on to another example. Use the laws of logarithms to write y as a function of x for each of the following, then state the domain of the function. Okay, so looking at the first one here, log of xy equals 2 log x minus 3. Okay, so we can already see a little bit of a hint of a product rule there, right? So what if we kind of expanded that, right? Log of x plus log of y. That's what the product rule says. And then on the right side, we have 2 log of x minus 3. Okay, well, if I want to write this as y as a function of x, I want to isolate the y. So let's keep the log of y on the left side and bring log of x over to the other side. So I can write this as log. And why don't I write this as x minus 3 and make that squared? Just we're saying, use the power rule in reverse, bring that that coefficient of 2 to the exponent inside the argument. And this log of x here will come to this side as log of minus log of x. Okay. And then that allows me to use the quotient rule on the right side. So I can write this as log of x minus 3 squared over x. And that's equal to log of y. And now that you have log of y equals log of another argument, both logs have a base of 10, I don't need the logs anymore. Just write it as y equals x minus 3 squared over x, right? It's as if I'm going to say, hey, take the 10 to the power of both sides now, and that will just cancel with the logs, right? And that leaves me with y equals x minus 3 squared over x. Okay, and what is the domain of this function? Well, one thing, x cannot be 0, of course. Denominator would be 0. But looking at the logarithms, look at the logarithms, right? So we have this logarithm with x by itself, right? That says x has to be greater than 0. X minus 3 has to be greater than 0. So that means x has to be greater than positive 3. And so that dominates more than x greater than 0. So I'm going to say, hey, x greater than 3 is my domain. Okay. Why do I say it dominates? Because if I used x equals 1, it might satisfy this one, but it wouldn't satisfy this one. So any number greater than 3 will satisfy both x minus 3 as well as just x. So that works. Okay. So y equals x minus 3 squared over x, where x is greater than. Okay. Let's look at question B. log of y plus 3 equals log of y plus 1 plus log of x. So what can we do here? We can potentially, hey, use the product rule on the right side. We've got two logs at the same base. So if we did that, log of x times y plus 1. Okay, so that's something. On the left side, I still have log of y plus 3. Okay, so 3 is not a logarithm. I can't use a product rule on that. So no product rule there. Well, what if we bring both logs to the left side? So when I say, hey, log of y, take away log of x times y plus 1 equals, and bring the 3 over to the right, and it becomes -3. And then now I have these two logs here that I could, well, same base, I can apply the quotient rule, write that as one log, where y is the numerator and the denominator is x times y plus 1. And that's equal to -3. Now, what do I do in this case? Well, you treat this as like, the log of some argument equals -3. That says, well, 10 to the power of -3 equals whatever that argument is. So don't get all of a sudden confused with y and x's and y plus 1s, right? It's still a logarithm, and that logarithm equals to -3. So 10 to the power of -3 has to equal all of that stuff inside. So I can now write this as 10 to the power of -3 equals y over x times y plus 1. And that gets rid of the log, and now there's some potential to isolate for y. Okay, so how am I going to do that? Well, right, 10 to the power of -3 is 1 over 1,000. And here I have y over x times y plus 1. And then why don't I kind of cross multiply here, right? So let's write this as x. X times y plus 1 equals 1,000y. And then maybe I might have to expand this, right? So xy plus x equals 1,000y. And where am I going with this? Well, let's see. Let's bring this xy back to this side. So we have x equals 1,000y minus xy. Maybe I factor out a y, right? So y times 1,000 minus x, and that's equal to x. And then now I can, I can isolate for y now. So y will equal x over 1,000 minus x. So a little bit of algebraic manipulation going on here until you can get that y by itself. Okay, and so there you have it. There is your y in terms of x. Okay, and what about domain? What's the domain? Well, this argument here, x has to be greater than 0. Okay. X is an independent variable. That's all I really care about. So x greater than 0. And there you have it. So just more examples of simplifying expressions with logarithms. And then we're going to use all of these 4 rules that I presented to you here in the beginning in our next lesson. These rules here in our next lesson, 7.4, the final lesson that we're going to look at in chapter 7, 7.4, solving yet more equations, more techniques of solving logarithmic equations. All right, see you in the next lesson. Like and subscribe. Okay, bye-bye.